Everyone. So if you take a look at the balanced chemical equation for the combustion of hydrogen, you'll see that you need two hydrogen molecules to react with one oxygen molecule to provide two water molecules. So kind of drawing that out, here's a hydrogen molecule and here's another one. Those are two of them. And here's an oxygen molecule and two water molecules. You should be able to see that the number of atoms of each element are conserved. There are just as many hydrogen atoms, four of them here, as there are here, and two oxygen atoms on the left and two oxygen atoms on the right. When we balance an equation, we not only end up balancing and conserving the number of atoms, but mass is also conserved. Because we have just as many atoms on both sides of each element, we'll have just as much mass because atoms have mass. So mass cannot be created or destroyed. It's conserved during a chemical reaction. But the number of molecules is not always conserved. So we saw here that there were two molecules of hydrogen and one molecule of oxygen, a total of 3 molecules. But at the end of the reaction, there were two molecules. Because the molecules ended up getting bigger, there ended up being fewer of them. So oftentimes there's not a conservation of the number of molecules. The ratio that we saw in this balanced chemical equation, described by these coefficients 2, 1, and 2, that shows the ratio between the molecules of each other, but ultimately it shows the ratio of moles versus each other as well. And I'll prove this to you. If we have two molecules of H2 to one molecule of O2, then if there were 10 molecules of O2 reacting, there would be twice as many molecules of H2, 20. And there would be twice as many molecules of H2O formed. And then if there were 1 times 6.02 times 10 to the 23 molecules of O2 reacting, there would be 2 times 6.02 times 10 to the 23 molecules of H2 reacting, twice as many. Ditto 2 molecules of H2O, 2 times 6.02 times 10 to the 23 molecules of H2O formed. The ratios are consistent. You should have a 2 to 1 to 2 ratio, whether you're dealing with individual molecules or large numbers of molecules or moles. You see, this 1 times 6.02 times 10 to the 23 is 1 mole, because a mole is 6.02 times 10 to the 23 of something. So when 1 mole of O2 reacts, there are 2 moles of H2 reacting and 2 moles of H2O being formed. That's the kind of a key point here. In the balanced chemical equation, those coefficients stand for the number of molecules versus each other, or moles versus each other. So we should see that oftentimes the number of moles of substance are not conserved. Here you started with 2 plus 1, 3, but then you ended up with 2. But let's actually keep track of the mass of these numbers of moles. If you had 1 mole of O2 reacting, that'd be 32 grams. If you had 2 moles of H2 reacting, that'd be 4 grams. And if you had 2 moles of H2O being formed, you'd have 18 times 2, 36 grams. You'd have, at the beginning of the reaction, 4 plus 32, 36 grams. And at the end, you'd have 36 grams. Mass is conserved. There should be just as much mass at the beginning and end. Mass is not created or destroyed according to the law of conservation of mass. All right, so an important point was moles is conserved. Moles is not conserved, but these ratios in the balanced chemical equation are for moles versus each other. We're going to use that as we do our math for the next couple weeks. So let's use that balanced chemical equation to say how many moles of water can be produced from the complete combustion of 8.0 moles of O2. All right, so if you're reacting 8.0 moles of O2, how many moles of H2O can form? So now we can use a unit conversion factor to get out of moles, top and bottom, and into moles of H2O. That unit conversion factor is going to have the coefficients from the balanced chemical equation. We saw that every time 1 mole of O2 reacted, 2 moles of H2O were formed. These numbers are exactly in the balanced chemical equation. Every time 1 mole of O2 reacts, 2 moles of H2O are formed. From those coefficients, these are coefficients, we are going to get this mole ratio. That's going to be in the center of every one of your calculations in the next couple weeks. Remember, moles is your happy place, and to convert from an amount of one substance into an amount of a different substance, you need to multiply by the mole ratio. So if you reacted 8 moles of O2, you should get twice as many moles of H2O formed, 16. So just kind of in a general equation, for a general reaction where you have a substance that you're given information about, whether reactant or product, and you want to get into a substance that you want information about, whether reactant or product, you need to use the coefficients that were in front of them in that balanced chemical equation and plug those into that mole ratio to convert from moles of one thing to moles of another. All right, next question. How many grams of water can be produced from the complete combustion of 64.00 grams of oxygen? All right, so you have grams of oxygen, 64.00 grams. You want to get into grams of water. Now, you can't go directly from grams of oxygen into grams of water very easily. Instead, you need to go into a rest-stop unit, something that allows you to convert from an amount of one substance into an amount of another. Just like in the last problem, we saw that you could do that using the mole ratio. If you go from grams of oxygen into moles of oxygen, then you can use the mole ratio to get into moles of water. This is the only way we're going to use in this class to get from amounts of one substance into amounts of another substance. And then how many moles of water you can go into grams of water. So we'll set the problem up starting with grams of oxygen. We'll convert into moles of oxygen. We know that for every mole of oxygen, there's a certain mass of oxygen, the molar mass of oxygen. So that's on the periodic table. 2 times 16.00, that's 32.00 grams of oxygen per mole of oxygen. So grams of oxygen is on top and bottom, it's canceled. Now we're into moles of oxygen. Now we want to go into moles of water. So to do that, we need to use that mole ratio. Cancel out moles of oxygen by putting that on the bottom, and then get into moles of water by putting that on the top. Where do these values come from? Just like in the top problem, it's going to be from the coefficients in the balanced chemical equation. For every 1 mole of oxygen reacted, there's 2 moles of water formed. So we'll plug that in here. For every 1 mole of oxygen reacted, there's 2 moles of water formed. So now we're into moles of water. We can get into grams of water by putting moles of water on bottom and putting grams of water on top in the next unit conversion factor. Per mole of water, there's a certain mass of it, the molar mass. On the periodic table, it's 18.00. And so we'll get 72.08 grams of water are needed to react with 64.00 grams of oxygen.